Okay, well, I guess we might as well get started. It's a pleasure to introduce my colleague, David Gosset.
Thanks, Mark. Thanks for coming on the last day. Very good morning. Thanks to the organizers for having me. So this talk is joint work with S.Bravyi, Robert Koenig, and Munich. And it's about approximation algorithms for quantum body problems. So I'm going to start by just saying some very general, possibly boring things, which, you know, so quantum many-body systems that appear in nature have local interactions, like molecules or superconductors or materials. And those interactions are described in physics by a local Hamiltonian, which is a Hermitian operator that describes the interactions. So the fact that it's local is expressed mathematically by the fact that the Hermitian operator is a sum of h sub c, so it's a sum over some index c of this little hc, and the little hc involves maybe interactions between just 2 or 3 or a small number, usually just 2 particles at a time. Now, computing properties of physical systems like this, modeled as local Hamiltonians, is generally a hard computational problem. And this was formalized by Alexei, who noted that if we have a n-particle quantum system with local interactions, and we ask some formal version of the problem of approximating the ground energy, then we can do this as an intractable quantum constraint satisfaction problem. So just to be a little bit more precise, if we have a system of n qubits, and we're given 2 numbers, well, let's say one number a, which is a real number, and then also a precision parameter epsilon, so we have sort of 2 thresholds, a and a plus epsilon, and we want to know, is the ground energy below a or above a plus epsilon, so in this green region or in the blue region, and we're promised that it's definitely not in this black region. So if it's given a Hamiltonian, ground energy is either down here or up here, we want to know which one is the case, then Kitaev proved this is complete for a complexity class called QMA, which is the quantum analog of NP. So this is a class of decision problems that can be solved efficiently using a quantum computer and given a quantum proof from some all-powerful prover. All right. So this kind of makes you think that we're going to have a really hard time understanding the properties of materials and molecules and things like this, or it might. Let me also mention that this local Hamiltonian problem, it remains intractable even for systems with 2-qubit interactions. So this, you might say, well, what does local mean here? It could mean 3 local, 4 local, but it's hard even when you only have 2-qubit interactions. And in fact, it's also known to be hard even with much stronger restrictions on the geometry. So for example, if the Hamiltonian describes interactions on a 2-dimensional grid, it's still hard, or even on a 1-dimensional line. And in fact, it's known to be hard in 1 dimension with higher dimensional particles, so not qubits anymore, but the local Hilbert space is now d-dimensional for some constant d. But this is hard even if the Hamiltonian is translation invariant. So the local term that describes the interaction between nearest neighbors can be the same everywhere, and the problem is still hard. And it's also true for things that look like fermions hopping on a 2-dimensional grid with a segment-dependent magnetic field. So basically, any sort of natural restriction you might think of, or that might be closer to what arises in physics or chemistry, usually you can find some kind of wiggle room to encode some hard problem into that restricted type of interaction. And so then you can ask, well, can we hope to efficiently compute good approximations to the ground energy? And here the key word is approximation, right? So this sort of says we're not going to be able to compute ground energies efficiently to a good precision, but maybe we can ask about approximation. Okay, so that's kind of the context. And so now I'm going to talk a little bit about hardness of approximation, which is we're going to slowly connect maybe a little bit to the subject matter of this question. Okay, so hardness of approximation. So now we're asking about not computing a precise estimate of the ground energy, but instead asking for an approximation. And so we have our local Hamiltonian, but even we're sort of already dead in the water in a way, because we know from the classical PCP theorem that it's NP hard. So NP, before we were talking about QMA hardness, but both QMA and NP are, sort of kill this idea of efficient computation. Okay, so it's NP hard to compute an estimate of this, let's say, the ground energy within an error that scales with the number of terms. Okay, so that sort of already kills the idea of efficiently computing approximations in this sense. It has been conjectured that, in fact, this problem might even be harder, like QMA hard, but either way, it's, again, sort of bad news. Okay, so that's sort of bad news for approximations. So then what is done in practice? Well, there are these variational methods. So what can you do? You can find some set of states S that can be represented efficiently on a classical computer. Okay, this is highly non-trivial. Most quantum states, let's say of n qubits, do not have efficient classical descriptions. But nevertheless, we can try to find some interesting set of states that can be represented efficiently. And then we can try to minimize the energy over that set of states. And for spin systems, this is called mean field theory. And typically you would optimize over product states. For like electronic structure in chemistry, this would be called Hartree-Fock theory, and there you would optimize over fermionic states called Slater determinants that I'll describe later. So this is kind of a program that has been applied in these situations, and kind of the maybe overall motivating question for our work is like, how well do these methods perform? And so there's two questions that we want to ask. One is, what is the best energy attained by some state from this family S? So this is not a question about efficiency. It's just a question about what is the best energy in that variational family. And the second one is the question of efficiency. What is the best energy of a state that can be computed in polynomial time? We're talking about classical computers, so on a classical computer. Okay, so this is the motivation, you're going to see that the answers to these questions, although I've sort of tried to motivate things by like what people do in practice and like, maybe you care about materials, the answers to these questions are going to be so depressing that nothing we do is going to be useful as a method to like study properties of materials. And really our perspective is more like that of computer scientists to understand this sort of worst case, complexity of this problem. Okay? All right. Okay, so what is our approximation task? Let me be a little bit more precise. So I was talking about ground energies before, but now I'm going to just flip the sign of the Hamiltonian and talk about maximal energies because it's going to make it easier to define the problem that I want to describe. So we're going to maximize the energy of the Hamiltonian now. Lambda max is just going to be the maximum eigenvalue, and that's what we want to approximate. So our goal is going to be to compute an estimate lambda. We're going to require that the estimate is always upper bounded by lambda max. And we want the ratio of lambda divided by lambda max to be as close to 1 as possible. So this ratio, we'll call it the approximation ratio, we want the best possible approximation ratio. That's our goal. Now, you might notice that if we shift the Hamiltonian by a term which is proportional to the identity, that's a very trivial thing. It doesn't change the complexity of really any real-world task, but it can shift the maximum eigenvalue and it can shift our estimate both by a constant, and so then it can change this approximation ratio. So in order for this to be sort of a well-defined metric, we need to fix some convention that doesn't let us shift by multiples of the identity. So what we are going to do in this talk is we're going to consider traceless Hamiltonians, meaning this identity term is 0. Okay? We're also going to restrict our attention to systems with two-body interactions, interaction between two particles at a time. That's the task. Are there any questions about that? Okay. So let me mention some previous results. So there are a few different, there's sort of two main, well, there's a few different settings where you can study this problem, and there's different answers to these questions. And so one setting is you could consider Hamiltonians where all the terms are positive semi-definite. Okay, this is not the case of traceless Hamiltonians. So if you have k local terms and positive semi-definite terms, there's a theorem by Gaussian and Temme, which says that the product state achieves an approximation ratio, which is 1 over 2 to the k minus 1. So for example, for two local qubit Hamiltonians with positive semi-definite terms, you can get an approximation ratio of 1/2 using product states. And there are examples where that's the best possible, so this cannot be true. Okay. And I should also mention that Aaron and Fernando gave a polynomial time algorithm for dense instances of this problem, which gets a error that's proportional to the number of terms. Okay. Another situation you might consider is when the terms are not positive semi-definite, but let's say they're proportional to n qubit Pauli algorithms. And again, Aram and Ashley Montanaro showed that there is a product state, you can compute a product state efficiently, which achieves a 1 over n fraction of the 1 norm of these coefficients. Okay, so this is not the same as the approximation task that we're considering, because we want the ratio to the maximum eigenvalue, whereas here the ratio is computed to the 1 norm of the coefficients. Okay? So it's a slightly different approximation task that's being considered. Okay. All right, so those are some previous results, and now I'm going to describe the classical template that we are going to extend to the quantum case. So this is now sort of the template for what we're going to do. Okay. So suppose you have, remember we're talking about traceless and two local Hamiltonians, but suppose you have the classical case, so it's diagonal in the standard computational basis. So it can be expressed in terms of Pauli Z operators acting on the n qubits. So here we have a quadratic term and a linear term, and the fact that it's traceless means that this matrix B has no diagonal elements. Okay, so this is a classical quadratic binary function, where it's a matrix which is just diagonal and has the function that's diagonal. Okay, right. So although I expressed it as a matrix, our goal is to compute the maximum eigenvalue. Since it's diagonal, we can just look at the diagonal entries, and those are described by this binary quadratic function. Okay, so it's not, it's an easy fact that computing the maximum of such a function is an NP-hard problem. Again, so carrying on what we saw earlier. Also kind of trivial fact is that we can restrict our attention to the case where this linear term is 0. And the reason for that is that we can add just some extra variable y, and it suffices to maximize this homogeneous quadratic function, and show that the maximum is the same. Okay. Now here's the first maybe interesting fact, which is that there is an efficient classical algorithm which gets a ratio to the maximum of this classical quadratic function of 1 over log n. Okay, so the approximation ratio that can be achieved efficiently according to this algorithm is at least 1 over log n. What is this algorithm? Well, it's based on semi-definite programming relaxation along the lines of Bowman and Williamson. So you have this hard optimization problem, which is maximizing the quadratic function. Now you relax it, so you sort of work with the pseudo-expectations as was described earlier. You have this matrix X that describes those pseudo-expectations, and so you cap this relaxation as a semi-definite program, which can be solved efficiently, and then you round back to the original problem. And this is not, if you know Gomez-Williamson, that gets a ratio of 0.8 something from this max cut problem, whereas here you get 1 over log n, and that's sort of related to the fact that in this setting, we're sort of working the traceless case, whereas in that setting, the terms are positive semidefinite. So you can think of the difference between the reason why here you get 1 over log n and there you get a constant is sort of related to the fact that there's these two settings, one where you have positive semidefinite terms and one where you have traceless terms. And the ratios that you get in one case are constant, and the ratios you get in this case depend on that. Okay, so this is the template for what we want to do. And, so maybe the next important and non-trivial fact is that this ratio, you could ask, how good is this? Well, it's not far from optimal if you are willing to assume that NP-hard problems can't be solved in quasi-polynomial time. If you don't know what this means, just think that it's polynomial time. It's not quasi-polynomial is almost exactly the same as polynomial time. So what was proved by Aurora et al. Using the PCD theorem is that there is some constant between 0 and 1 such that it's intractable to achieve a ratio of 1 over log n to the gamma. So we don't know what the constant is, but, 1 over log n to 1 over maybe third log n, or log n to 1/3, or whatever this constant is, there's not that big of a gap, and it's sort of hard to reason about what the gap is since we don't know the gamma. Okay, so this is our template, and now we're going to try to extend this to quantum spin and fermionic systems. So there's two different cases we want to consider. So this is the table that I want to fill out in the rest of the talk. So here we have the classic case that we just discussed, binary quadratic function. Here we're considering approximating by bit strings. Of course, that's not an approximation in this case. The best possible bit string achieves a ratio of 1. We know that 1 over log n, or constant over log n, is efficiently achievable, and it's hard to achieve a constant over log n to some power. Yes?
So it's plus minus 1, right? Or...
Oh, yes, sorry, it should be, yes, it should be plus minus 1. Thank you. Okay, so now we want to talk about qubit systems and then fermionic systems. And maybe I'll just mention at this juncture that, we talked about, or Aaron mentioned polynomial optimization, and of course this is some example of quadratic polynomial optimization, and these are some quantum generalizations. And in fact, this is maybe the most obvious generalization, but this one I want to emphasize is kind of interesting, or maybe more interesting than that one. And in fact, this includes both of these as special cases. So maybe the most interesting thing I can convey is that in terms of polynomial optimization problem that is quantum, this is kind of maybe an interesting thing that you might not encounter unless you had thought about fermions. Okay, so we'll get to that. The first thing is two local qubit Hamiltonians, and we want to talk about this mean field theory, which is optimizing over product states. So we have an n-qubit traceless 2 local Hamiltonian, which means that we have a Hamiltonian which is quadratic in the single qubit Pauli operator. So we have x, y, and z for each qubit. So we have 3n, and we're going to label them pi from 1 to 3n. So we have a linear term in the p and a quadratic term. Remember that in the classical case we could get rid of the linear term, and it's the same thing here. You can use a time reversal map to show that the spectrum of this Hamiltonian is the same as that of the original. This is purely quadratic. Okay, so without loss of generality, we can set h1 to 0 when we're talking about approximation ratios and algorithms. So then we have our two questions, right? What is the best energy attained by a product state? And what is the best energy that we can compute efficiently of product states? So, okay, so there's kind of an interesting theorem due to Lieb from 1973, which is that there is always a product state that gets a ratio of 1/9. Okay? You'll notice that 1/9 is bigger than 1 over log n, right? So the hardness result, computing this product state is going to be hard. We already know that from classical hardness, which carries over into this case. But this is an existence proof and does not give you an algorithm that's efficient. And I think it's kind of an interesting proof, even though it's like, so we give a little shorter version of this proof, which is just completely trivial, and that I want to show to you now because it's kind of amusing, and because we don't have a version of this in the Fermionic case. Okay, so here's the amusing little proof. So let's say you just give me any n-qubit state psi. Okay? Now I'm going to just add noise to that state. Okay? I'm going to apply a depolarizing channel to every qubit. You can think of this as there's a parameter in this channel delta, and when delta is 0, that corresponds to just replacing the state with the identity. So replacing it with the completely mixed state. When delta is 1, you're doing nothing. Okay? So this is, you know, completely noisy when delta is 0, and when delta is 1, you're doing nothing to the state. And you're just acting on every qubit individually. It's a tensor product of depolarizing channels on each qubit. Okay? And so you take this psi and you screw it up by sending it through this depolarizing channel, you get some rho psi. And the depolarizing channel has the property that when you compute the expected value of a Pauli at the output, it's, you know, because we have two local terms, we get a delta squared here. If this were just one of these p's, we would get a delta. If there were k of them, we would get deltas of k. So every Pauli operator gets attenuated by a factor of delta. And since our terms are too local, we get delta squared. Okay? So the output state has energy, which is delta squared times the input state, okay, for any delta. So this is just a way of adding noise to a state and relating the energy of the noisy state to that of the original state.
What's capital D delta?
This is a depolarizing channel, so you can.
Is there a formula for it? Or?
Yeah, there's a formula. So you can think of it as like the like we can define. So this is a single qubit channel. So we can think of its action on like a basis of 2 by 2 matrices, and it acts on the identity. Gives you back the identity. And it acts on any Pauli matrix, like if P is X, Y, or Z, it just gives you back delta P. So that's the fact that I'm using here. Okay. But what's interesting here, so not only can we relate the energy, but when, if you choose, so we're going to choose this parameter delta to be 1/3. There's a magic fact about 1/3. So when you choose to be 1/3, this delta squared becomes 1/9, and that's the 1/9 we're getting here. And there's one more magical fact here, which is that when you choose it to be 1/3 or less, the channel becomes entanglement breaking. And what that means is that when you apply it, or one thing that it means is that when you apply it to n qubits, you get a separable state, which is a convex combination of product states. So we're adding noise to any state, we get a separable state with energy 1/9 of the original state, and that implies that by convexity there is a product state with energy at least 1/9 that of psi. Now we could have plugged in any state here, but of course we're going to plug in the maximum eigenvector to get a product state with 1/9 of the maximum. Okay, so this is like a kind of simple but maybe interesting argument. Okay, so you can take the product state to have some specific form, but maybe the more interesting thing on this slide is that you can just think, if you like, you can think of this depolarizing channel as you just choose a random X, Y, or Z Pauli basis for each qubit, and then measure in that basis, and then you just prepare the state that you measure. Okay, so that always outputs an empty product state, and the average energy will be 1/9 maximum. Okay, so this answers the question of what is the, at least it gives some bound on the best product state. We actually don't think, so we believe that the right answer is 1/3, but we can't prove it. We have a proof in the appendix of our paper which improves the 1/9 to 1/6, but it's not in quite the same setting. So you have to replace the maximum eigenvalue with the norm, and you have to replace the expected value, like you replace everything with norms. So the lambda now becomes either the maximum energy or minus the maximum energy of the product state. So everything, if replace the maximum eigenvalue with the norm and the maximum product state energy with the maximum absolute value of product state energy, you get a 1/6 using a much more involved argument that involves both this entanglement breaking thing, this is just for Aram, and this Hastad, this Hastad thing that was used.
Oh yeah.
Yeah. Anyways, so you can get 1/6. All right, but getting to the 1/3 is an open question. We don't know how to do that. Okay, so the second question was, what is the best efficiently achievable approximation ratio? And there we can match the 1/log n that you get in the classical case, essentially using the same algorithm, but obviously modified just a tiny bit to handle quantum states. So again, we have our Hamiltonian, which is quadratic. We can define, the maximum energy can be expressed as a trace of this C matrix, the matrix of coefficients, against a matrix of expected values, M. These are the expected values of Pi, Pj in the true maximizing state psi. So now, of course, following this program that we've been discussing, you would replace this with just a general matrix that satisfies all the constraints that we know this matrix should satisfy. So in particular, this is positive semi-definite. It has ones on the diagonal. Now we can consider a relaxation that just maximizes this trace over positive semi-definite matrices with ones on the diagonal, and that will give an upper bound to the true maximum energy. This is a semi-definite program, which you can solve efficiently. Okay, so then once you have that STP relaxation, then you can apply a rounding procedure to map it to a product state, essentially. So at the end of the day, you want to take the output of your STP and obtain a tensor product of quantum states with some energy that's 1/log n that of the STP. And this really just does follow Char-Garden-Worth's procedure and with some small modifications. Okay. So that's the second line on this table. So we know again that it's just from the classical results, if this is a special case of this, the hardness carries through, that you can't beat 1/log n to some power. We can match the 1/log n approximation ratio that can be achieved efficiently. And mysteriously, there's always a product state sitting well above that hardness threshold. And it's just hard to compute in general. You can get at least one line. Yeah.
What's the best upper bound? 1/2?
Upper bound to this quantity?
Are there Hamiltonians where the product state will never? I'm guessing you don't know Hamiltonians where where a product state won't achieve more than 1/9 of the energy, but you could get
So we know examples where
it gets 1/2.
where it gets 1/3.
1/3.
Like 1/3, I think is the best possible. There are examples where you can't do that anymore.
Okay.
But we think 1/3 is the way.
Is that that's not anti-ferromagnetic?
Just on 2 qubits, you can define it. Okay. So now we're going to go to this third case, which generalizes both of these, which is the two-body fermionic Hamiltonians, that describe the electronic structure and all things and so on. By the way, I just want to comment again on the fact that, if you were an actual person doing material science, you would be just completely unhappy with this, right? Because even if you could compute this hard to compute state that gets 1/9, it's if you're off by the true energy by a factor of 8/9, it's not so good, right? But we're still going to push forward. All right, so two-body fermionic Hamiltonians and Hartree-Fock theory. I realized that this next set of slides is going to be weird because maybe you don't know what Slater determinant states are, so I'm going to give this description of Slater determinant states and then tell you why that's not the right thing to do. And you're supposed to already think that it's the right thing to do. But anyways, maybe you can just zone out, or it's only going to be a couple of slides. Okay, so what is a Slater determinant state? So first of all, the Hilbert space of n fermionic modes is 2 to the n-dimensional space. It's the same Hilbert space as that of n qubits. Okay, so everything is in an n-qubit space. It's just we're talking about now writing things in terms of different operators. So if you like, you can just think of the basis states as being labeled by bit strings again. And we have these operators that create or annihilate a 1 in a certain position. Now, a Slater determinant state is some kind of fermionic analog of a product state. So, in particular, we can define some new fermionic modes that are obtained from the old ones by some linear transformation where the coefficients are drawn from a unitary matrix. And then a Slater determinant is just acting on, like, the vacuum state are all zeros by applying these new fermionic modes. So for any choice of unitaries, these are n by n unitaries. These are very small unitary matrices. We're living in a 2 to the n dimensional space. So we can define new fermionic modes for any choice of n by n unitary, and that defines a Slater determinant state. We apply k of these. Okay, so this is some interesting set of states. This is used in quantum chemistry. What are the Hamiltonians? Well, again, we might have a constant term, we might have a linear piece, and we might have a... Okay, so linear in this case really corresponds to quadratic. And quartic, like if you want to describe two-body interactions, then you really need to have a quartic Hamiltonian. So two-body in this case, everything gets doubled. Like for example, the number operator, which is, well, maybe a... Okay, so the eigenvectors of this kind of Hamiltonian are Slater determinants, okay? So this is why you might think that Slater determinants, sorry, the eigenvectors of this non-interaction piece are Slater determinants. So just like in the spin case, we had a linear term and the eigenvectors are product states, and then we had a quadratic term, and then we try to approximate by product states. So here we have a linear term, the eigenvectors are Slater determinants. We have, or sorry, not linear, quadratic term, and then the quartic term, we might try to approximate the grounds to the maximum eigenvector by Slater determinants. It's sort of a natural thing to do. This generalizes this classical case that we talked about, because you can represent AJ dagger AJ as 1 minus CJ over 2. So you could just make this replacement everywhere and get a Hamiltonian of this form from a classical binary optimization model. So then you can ask, well, can we efficiently compute a Slater determinant which achieves this one over log n approximation ratio generalizing the classical binary quadratic notation? And the answer is actually no. So that's why Slater determinants are not the right thing to do here. Even if you're well, let me continue. So there is a traceless fermionic two-body Hamiltonian where you can't do better than 1 over n. Okay, so this is a generalization which does not work. I'm not really going to describe what I mean, there's some simple example, and you can show that you can't beat 1 over n. Okay, so the Slater determinants fail, but there is a generalization of Slater determinants which is both more beautiful and appears to work better. So, there's a thing called Fermionic Gaussian states that I want to describe now, and if you just zoned out the past few slides, this is the, wake up if you like. So what's interesting is that for this toy example I just told you where Slater determinants fail, like the energy gets only a 1 over n fraction for these Slater determinants. In that case, these Fermionic Gaussian states that generalize Slater determinants actually get a ratio that approaches 1. So in this example where Slater determinants fail, the Fermionic Gaussian states succeed sort of in an amazing way. So it gives us some hope that maybe this is the right consistency. So let me mention what these states are. So we have our fermionic creation annihilation operators. It's going to just be convenient, and it's going to make all of our formulas more simple if we work with Majorana fermion operators, which you can think of as being like the real and imaginary parts of these fermionic creation annihilation operators. And so when we do this transformation, this is just a new set of operators. There's 2n of these operators. They're Hermitian, and they satisfy the anti-commutation relations of the Cliff dot. So we're going to write our Hamiltonian in terms of these Majorana operators. Okay. So So a unitary, remember we're talking about a 2 to the n-dimensional Hilbert space, and we can define unitaries in that space. And such a unitary is Gaussian if under conjugation it maps each of these Majorana operators to a linear combination of Majorana operators. So this is a subset of n-cubic unitaries, which is very special. And the types of states we're going to consider are the Fermionic Gaussian states, which are just prepared from all zeros by applying a Gaussian unitary. Okay, so this is a very special family of quantum states that live in an n-qubit Hilbert space. Okay. Right. So these are more general than Slater determinants, but they can be efficiently represented and manipulated on a classical computer, which is very unusual, right? I mean, it's a very special thing. There's not many families of quantum states, like maybe in the stabilizer states, that's another example of a rich family of n-qubit states that can be manipulated and efficiently on a classical computer. There's really not much more than that in the Gaussian states. Okay. Right. So I already mentioned that if you have a quadratic Hamiltonian in creation annihilation operators, it looks like this, where you always have a annihilation operator matched with its dagger. So this conserves particle number, because you destroy a particle, you create a particle. And then the ground state is always a Slater determinant. Fermionic Gaussian states do not conserve particle numbers. They don't have a fixed particle number. But they describe more general ground states of Hamiltonians which are quadratic in the Majorana operator. So this includes that as a special case. So they don't necessarily conserve like Hamiltonians, even in the case where the Hamiltonian conserves particle. So like that example I gave before, this Richardson model, where Slater determinant states fail, the Hamiltonian conserves particle number. It has a symmetry. So the maximum eigenvector certainly has a fixed particle number. But we saw that Slater determinant states fail, even though these Fermionic Gaussian states succeed like in a kind of dramatic way. So that's kind of an interesting lesson. Okay. So now let me just set up the problem and then we'll be done. So the Hamiltonian we're going to consider, we have a quadratic piece in the Majorana operators, we have a quartic piece, this describes two-body interactions. This has as its ground state Fermionic Gaussian state, and we're going to consider optimizing over Fermionic Gaussian states to achieve some approximation to maximum optimization. I should mention that this generalizes both the classical quadratic binary optimization and the qubit generalization that we saw in the previous part of the talk. And the way that you can see that is you can take a Hamiltonian which is a two local n-qubit Hamiltonian. So this now involves the Pauli operators x, y, and z. And you can replace each qubit with 3 Majorana modes, C1, C2, C3, and you can make the following replacements. So you just take your n-qubit Hamiltonian that involves these x, y, and z on each qubit, and you just replace in this way for each qubit. Okay? And if you do that, you get a Hamiltonian that has 3 n Majoranas. And it turns out, I mean, it's not completely trivial, but it's not too hard to see, that it has the same spectrum of H, but now you've added a whole lot of multiplicity. Okay, so somehow this is the most general of the optimization problems that we talked about. Right. Oh, and as before, you can get rid of this linear term by some kind of time reversal map. So in other words, there's always a Hamiltonian H prime which has the same spectrum of this as this, but which is homogeneous in quartic. Okay, so now we can ask these questions like, can we efficiently compute, we have this quartic Hamiltonian, can we compute a Gaussian state which achieves a 1 over log n approximation ratio? And so now, right, so let's look at what is the expected value of this Hamiltonian in a Gaussian state. So here's our Hamiltonian. We can ensure some kind of symmetry of these coefficients, just using the commutation relation of these operators. Okay, so for any quantum state rho, we can define a covariance matrix, which is the expected value of I, Cp, Cq. P is not equal to Q, and then 0 on the diagonal. This matrix is always real and antisymmetric, and its norm is at most 1. But Gaussian states, they are like, you should think of them as being like multivariate Gaussian functions. They are completely determined by the covariance matrix. And you can compute higher order expected values, like this expected value of 4 things. This should be trace of rho, not h. And these higher order things can always be computed as in terms of the covariance matrix using a thing called Wick's theorem. So this is this formula is already enough to compute the expected value of h in any Gaussian state as a function of the covariance matrix. And when you do that, you will get an expression which, what it says is that the energy of a Gaussian state is now a quadratic function of the entries of this covariance matrix, which is a real antisymmetric matrix of norm at most 1. Okay, so now we have an optimization problem where the variables are these entries of the covariance matrix. Okay? So we can describe this as like maximizing the quadratic function of the matrix elements of this matrix, subject to a constraint that the matrix is in this linear subspace of real antisymmetric matrices and has a norm constraint. And, this has been studied in the optimization literature. So if you have some linear subspace L and a function that is quadratic in the matrix elements of this variable and a norm constraint, this thing has been called in the literature quadratic programming with orthogonality constraints. And conveniently for us, it was shown by So that you can get a 1 over log D approximation ratio where D is the dimension of this matrix X. Okay? So this is just a very general fact about this quadratic programming with orthogonality constraints, which lines up perfectly with our optimization over Gaussian states. Okay. So putting this together, what it says is that we can always compute a Fermionic Gaussian state efficiently that gets a 1 over log n ratio to the maximum Gaussian energy. Not the maximum energy, the maximum Gaussian energy. Okay? So the ratio we get is R over log n, where R is the ratio of the Gaussian energy to the maximum energy. And so now we have to understand what that is. So we have not answered that question yet, right? Like for the qubit case, we know that the maximum product state divided by the maximum energy is at least a 9. But here we haven't addressed that question. And in fact, we don't know the answer. So this is the missing link of our whole story, which is that we're only able to prove a really weak lower bound, that R is 1 over n log n. So this Gaussian energy, as far as we know, could be like down by a factor of 1 over n. And that's really disappointing. And so sort of a question that we have is like, can we lower bound this R by constant? And we don't know the answer. And what's missing maybe is some kind of version of this. Remember, we had this Lieb's theorem that has this very simple proof where you add noise to some state and you get a separable state that has energy 1 not the one we started with. This was this very simple argument. We don't have that argument in the Fermionic case. And maybe, so, understanding fermionic analogs of attainment breaking and whether or not this argument can be made in the Fermionic case is kind of an interesting question. I should mention that some people have sort of barely touched upon these questions and have characterized convex mixtures of Gaussian states, but the characterization is sort of hard to work with. It's similar to the K extendability characterization in certain states. Okay, so this is the table now. There's this, we don't know what this R is, and we have this lousy bound here. But again, I want to just summarize by saying like there was a lot of details here, and maybe the summary is that we have this like quadratic polynomial with binary variables, and there's a natural qubit extension where you replace the binary variables with Pauli matrices. But then there's another natural extension which is not the same as this, and which generalizes it, where here, sort of the linear piece, we just want to optimize that. We map to the quantum case, we get Hamiltonian with ground states and product states. The linear piece here corresponds to free fermions, which are much more, there's sort of these quantum analogs of multivariate Gaussians, and somehow this is maybe an interesting analog of polynomial optimization. All right, so I'll end there. Thank you.
So is intuition or hope that, I guess it is hope, but is the current understanding that this class is large enough to get good approximation ratios? I mean, the Fermionic one?
The Fermionic Gaussian series?
Yeah.
So good approximation ratios for what?
For what you're saying. I mean, do you think the...
Like efficiently or?
No, just let know that this factor of 1 over n log n, that thing.
Oh, I see. Yeah, so I don't know. I mean, if you ask me like what is this
What is the
R,
expected answer?
like
Or is there...
I think there's a hope that it's constant, but I also think that would be like there's also like a maybe 50-50. I don't know. Yes.
Do you know? So a few things. So is algorithm. Does that work for like higher degree polynomials?
No. Or other.
You don't know of any one that does.
No, but I mean, it's also possible that that it does, and it's mentioned in the last. You know what I mean? Like
Sure.
We were very focused on this.
And then my other question is, what about like do you know about is it NP hard to find the best fermionic Gaussian state?
Yeah, because that includes as a special case the problem, like we can.
It includes like binary problems. It includes classical problems.
Well, yes. Yeah, that's one way to see it. Yeah. Yeah.
Would it help if in your SDP relaxation you go upper in the hierarchy? So you're just like in the Gomez-Williamson version, right? So is it like helpful to consider, I don't know, like 3,
Like to take these pseudo expectations
Right, yeah.
of larger and larger matrices. Yeah, I mean, I think, like I'm not really an expert in this area, but I don't know of any way to analyze what happens when we do that, I mean, in these cases. There's not, for the qubit case, you kind of have this, like, you kind of lose hope a little bit because there's this barrier of 1 over log n to the gamma, and, it's really, and in fact, for the classical case, the best thing we know is already 1 over log n, and that comes from the lowest level. So yeah, I guess the answer is I don't know. Yeah.
So sometimes approximation algorithms work better in practice or in the average case than the worst case guarantees. Is that the case without algorithms?
I really don't know. That's a good question. Yeah. Average case.
Questions? Thank the speaker again. We'll reconvene at 10.
Why would
I think